Hi, in this video, we will try to understand the concept of permutation. We will know how to interpret and solve problems involving permutation. We know that the permutation for n objects taken r at a time is given by the formula such that n is greater than or equal to r. But can you understand permutation with that formula alone? Well, it's a little bit abstract, right?
So, what is permutation? How do we find the permutations of objects?
Suppose we have 6 different potted plants and we wish to arrange 4 of them in a row. In how many ways can this be done? We can determine this if we arrange only 4 of them at a time, such as this one. Interchanging the third and fourth options, we get another arrangement. You can see that we have the same potted plants, but different arrangement. Each possible arrangement is called permutations. It involves taking a specific number of items from any group or set and see how many ways the items can be orderly arranged. And yes, order matters. What we are concerned about is the arrangement of the objects regardless of its composition.
Instead of writing the whole formula, people use different notations such as the following, and they all mean the same thing. There are basically few types of permutation. One is repetition is allowed, such as 3 to 3, and when repetition is not allowed, such as arranging 4 persons in a line. You cannot be first and second. The easiest to compute and solve is the permutation with repetition. Suppose we have the numbers 1, 2, 3, 4, 5, 6, 7, 8, 9. In how many ways can we have a 3-digit number? Well, if we will think about it, there are 1000 numbers from 1 to 1000. We deduct the numbers 1 to 99 and 1000, and we are left with 900. We also deduct the multiples of 10, and we have 810 numbers left. Lastly, we deduct all 3-digit numbers with 0 in it, and we have 729 numbers.
Similarly, since repetition is allowed, we have 9 possibilities for the first digit, 9 for the second digit, and 9 for the third digit, giving us, by the fundamental counting principle, 729 numbers. Generally, when an object has n different types, we have n choices every time. So, by the fundamental counting principle, we have n times n times n and so on, giving us the permutation is equal to n raised to the r power, where r is the number of times we are choosing n every time.
For the permutation where repetition is not allowed, we must decrease the number of possible choices every time. For example, in how many ways can we arrange 4 persons in a row? After choosing, say, person A, we cannot choose him again, right? So our first choice has 4 possibilities. 3 for the second, then 2 and 1 for the third and fourth, giving us 4 factorial or 24 possibilities.
But before anything else, the factorial function symbolized by the exclamatory mark means we need to multiply a series of descending natural numbers. Examples, we have 4 factorial is equal to, we also have 6 factorial. We note that it is generally agreed that 0 factorial is equal to 1. It may seem funny, but it helps simplify a lot of equations.
Now, back to our example a while ago. Suppose we only want just the 2 of them. Then, it would be the permutation of 4 persons taken 2 at a time. Then we have 4 possibilities for the first choice and 3 possibilities for the third choice, giving us 12 permutations.
This is also given by the formula n factorial over n minus r factorial. Substituting values of n and r, we have 4 factorial over 4 minus 2 factorial. 2 times 1 gets cancelled out, and we get 12 permutations. Can you now answer the problem earlier?
Suppose we have 6 different potted plants and wish to arrange 4 of them in a row. In how many ways can this be done? That's right! We are counting the permutation of 6 different potted plants, taking 4 of them at a time. Thus we have 30 permutations.
Now, if we have the word 11, is there a difference when an object is repeated more than once in one permutation? How about if the permutation includes circular positions? Is there a difference with how we get the answer? Well, this could be good topics for another compute. See you compute!